Welcome back, students. In this video segment, we will cover two sections, sections 13.1 and 13.2. 13.1 is entitled Vector Functions and Space Curves, and section 13.2, Derivatives and Integrals of Vector Functions. This is where the course, I think, this is where the course starts to get very interesting, especially if you're a STEM major, which is probably most of you. Okay, so let's dig in. Let's take a look at what you've studied before, not everything, of course, and compare it to what we're doing in this section, in these two sections, with vector functions. Before, you studied, or up to now, you studied functions. Functions, extremely important quantities, objects in STEM field mathematics, and a function can be interpreted as, this is all old news for you, a sort of relationship where you have x as, say, an input or an element from your domain, and you allow y to be an output or a scalar or number from your domain, or your range rather, sorry about that. And graphically, of course, we get curves when we have something like y is some function of x. Input an x value, and output a y value. The y value we call f of x. Now we look at curves again. We look at functions that represent curves, but our point of view is a little different. Okay, so now, and let's do this in two space. Let's talk about this in two space, but this does generalize in three space, and we'll see a whole lot of examples in three space. But just for right now, let's say in two space, and we'll say now. I said earlier, I said before, so now we consider something called vector functions. Vector functions. Vector functions. Okay, and just like before, we're looking at curves, but these curves don't necessarily represent functions where y is a function of x. Okay, obviously this backward C-looking curve doesn't pass the vertical line test. It's not a function. One x value gives more than one y value. But this, in fact, can be a representation of something called a vector function. Instead of an input as an x value, we'll say an input as a t value. And it's very convenient, especially for our course, to consider t as time. T is time. So you name a time, or you input a t, and you have an output of r of t, and we'll consider r of t as a position vector. Doesn't have to be a position vector. Remember, vectors are not defined by their location in space, but we'll consider r of t as a position vector. Okay, so, and since it's a position vector, it shoots out from the origin. So our functions are traced out as position vectors of different size, magnitude, that shoot out from the origin. We don't go a horizontal x and a vertical y. We name a time, and at that time we shoot out to the origin, from the origin. And you can imagine as time goes on, let me do this in a different color here. As time goes on, we generate more and more and more and more position vectors. That one didn't turn out so straight. It's all right. So as time goes on and on and on, we generate more and more position vectors. Specifically, let's say in red, at t equals 0, our position vector is r of 0. And let's say at t equals, I don't know, 5 minutes, 5 hours, whatever, our position vector looks like the second position there. So as time goes on, we have a bunch of arrows shooting out at the origin, the tips of which generate or draw, if you will, a curve. Okay, of course, this all happens in 3-space as well. So in 3-space, you have a 3-dimensional curve, and that 3-dimensional curve is traced out by observing or taking note of a position vector from the origin. Position vectors in 3-space have an x component, a y component, and a z component. And as t goes on, and again, it's really convenient to consider t as time. As time goes on, we sweep out a curve in 3-space. And it is a function because one input of time gives you one output of a position vector. One input of time and gives you a one output as a position vector. In other words, you can't be at two places, two different position vectors at the same time, to bring up an old cliche. Let's take a look at some specific examples. Specific examples. Let's see here. What will be a good specific example? That's a good one. Let's look at a specific example that we've already looked at. We've already looked at a particular kind of vector function. Let's see if you can think of it what kind of vector functions we've looked at before I write it. And your hint is it's not planes. It's lines. Suppose we have the vector form of a line r equals the initial r sub 0, 0, 1 plus t times the vector, let's say 2, 1 is a direction vector. And just to remind you, we have r equals r naught plus t times v. Okay, this is a vector function. R is definitely a function of time, or t. I'll refer to it as time, even though it doesn't have to be time. So to graph this is very, very simple. The initial position vector, sorry about that. That was weird. Is the point 0, 1. So I'll draw that in red real thick here. So here's 0, 1, otherwise known as j, the standard basis vector j. So here's 0, 1. And to that we add multiples of 2, 1, the direction vector. So let's draw from the point 0, 1, the tip of this initial position vector. Let's draw a vector 2, 1. If I move over 2, 1, 2, I go up 1. So here is the vector 2, 1. And if I take r naught, and add different multiples of that position vector 2, 1, I generate a line. Okay, so this is a simple space curve. In fact, arguably the simplest space curve. Lines. Okay, we're not interested so much in lines in this section. We've talked about lines to death, not literally, obviously. Let's take a look at another example. Now, let's let r of t, position vector, equal the vector whose components are t, comma, t squared. Okay, or if you'd like, ti plus t squared j, using standard basis of vectors I and j. Okay, the r again is viewed as a position vector, The t and t squared, these are called component functions. It makes sense to call them component functions. First of all, they're components, and they are functions of t. So a space curve or a vector function can be viewed as a position vector, and it will have component functions. In 2 space, it'll have 2 component functions. In 3 space, it'll have 3 component functions. So this vector function is locked into R2. It is in R2 because the vectors are of the form t comma t squared, and those vectors are in R2. So what does it look like graphically? It looks very simple graphically. To graph a position vector, or a vector function rather, to graph a vector function, it's very common to take the vector function and write it as scalar functions of t. Okay, so if I pull out the components, then x is going to equal t and y equals t squared. Just like we did with lines, we had vector equations of lines, or we could remove the components of the vector equation of a line and form parametric equations of a line. Just like we have parametric equations of lines, we also have parametric equations that describe vector functions. So these are called parametric equations. A lot of students, in fact, I think 50% of students have studied parametric equations by now, either in pre-calculus and or in Calc 2. I don't teach those heavily, if at all, in either of those courses. So this may be, if you've had me for pre-calc and or Calc 2, this may be your first time with parametric equations. I don't teach them at all or heavily in those courses because it's very easy to present them to you in Calc 3. Parametric equations are a way of expressing the x and y values of a curve, or x, y, and z values of a curve, in terms of a third variable, t, very often considered time. And in that way, you have something called parametric equations. T is called the parameter. T is called the parameter. Okay, so let's take a look at x equals t and y equals t squared. Very often, to get an idea of what a vector function looks like, you'll take the vector function apart and put it in terms of its parametric equations, and then attempt to eliminate the parameter. If x equals t and y equals t squared, we could substitute the first equation into the second equation to get y equals x squared. Okay, and we know what y equals x squared looks like. Okay, I want to take out those axes I just drew because we kind of need the whole xy plane to graph y equals x squared. So back to my drawing board. We know what y equals x squared looks like. We learned about it. You learned about it years ago when you took algebra 1. Most likely, I think it's algebra 1 now that they draw parabolas and stuff. If not, you definitely looked at it in algebra 2. This is what y equals x squared looks like. It's a very simple parabola. Very simple parabola. Okay. However, this is not a graph of the vector function. It's not anywhere near complete. Not at all. Okay. The thing is, the vector function lies on this curve, but vector functions also have a direction along which this curve is traced. If you think about t as being time, t increases. Time always increases. Time never goes backwards. In general, you get the direction of a curve by considering what's happening with the coordinates x, y, and z, or just x and y if you're in R2, as time increases or as t increases. As t increases, this one's very easy. We have x equals t. We have y equals t squared. It's a terrible looking y. We have y equals t squared. So ask yourself, as t increases, what happens to x and y? Increases. In fact, just for this particular curve, all you have to answer the question, all you have to do to the answer to the question is figure out what happens to x. As t increases, x increases because x equals t. It's not always the case that as t increases, x increases. for every space curve. But this one's true. So the curve, the direction of the curve is from left to right, and we indicate that with arrows along the curve. You can visualize this as the path taken by a fly or a bug or an airplane or a missile or a UFO or whatever. The object stays on the curve, and as time moves on, the object moves along the curve as indicated with the arrow. Sometimes curves have starting points. This one doesn't. Since I haven't expressed any kind of restriction on t, that is, t is greater than or equal to 0 or anything like that, the curve represents the entire y equals x squared. Okay. If time started at, say, -1, then we would have the curve, we've only sketched that portion of the curve that starts at the point -1, 1. Okay. In any case, we can consider the curve as being the result of plotting a whole bunch of position vectors, r of t. Here's the negative part. R of t, which is composed of a horizontal component t and a vertical component t squared. Why? Because x equals t and y equals t squared. Okay. I drew this last picture just to emphasize to you that vector functions are considered graphs that are traced by shooting position vectors out of the origin. Ultimately, r of t, the position vector, shoots out from the origin. I want to look at a few more vector functions, and ultimately I want to get into 3-space, but for right now let's sketch. Let's say r of t equals the vector function whose components are cosine of t and sine of t. Okay. So we have 2 things to do, maybe even 3 things. Let's do this. For t greater than or equal to 0. When you graph vector functions, you have 2 or 3 things to do. If the parameter is restricted, that is, in this case, t is greater than or equal to 0 and t doesn't run through all real numbers, then you might want to consider a starting point for the curve. Okay. The other 2 things are the curve itself, along what curve does this particle lie if it's a particle moving through space, and direction. Okay, so let's see what's going on with this. I would like to eliminate the parameter from the parametric equation. So first I'll write out the parametric equations. X equals t cosine t, y equals sine t. Those are the component functions. And I want to eliminate the parameter. With parametric equations like this, a little bit of trigonometry goes a long way. If we take x squared and y squared and add them up, we get cosine t squared plus sine t quantity squared. And it's one of the first identities you study in trig. This is 1. Cosine squared t plus sine squared t is 1. So this curve, this vector function, lies on the circle x squared plus y squared equals 1. Let's see if I can do that. Here's x squared. This is going to represent x squared plus y squared equals 1. Let me move my axes sort of to the center if possible. That's about right. That's okay. So here's x squared plus y squared equals 1. X equals cosine t, y equals sine t. Where does this curve start? Okay, well, what's r of 0? R of 0 is cosine of 0, the vector whose components are cosine of 0 and sine of 0. Oops. Cosine of 0 is 1, sine of 0 is 0. So this vector function starts at the point 1, 0. R of 0 is that's I, that's the standard basis vector I. So this particle starts at the origin and then moves along the curve. Well, the questions should be: does it move along the entire curve? It doesn't have to. The entire circle doesn't have to be generated by this vector function. And does the particle move clockwise, counterclockwise, clockwise sometimes, counterclockwise other times? Well, there are a number of ways of figuring out the direction of a curve. One popular way of doing that is to separately sketch the component functions. Separately sketch the component functions. So here's on this little axis, set of axes that I've just drawn here. I'm going to draw the x component. I want to draw another set of axes. We're going to do the y coordinate too component. So let's assume that on the first set of axes, I want to graph x versus t. Second set of axes, y versus t. Excuse me. Okay, well, x equals cosine of t. X equals cosine of t. So the x coordinate looks like this if we were to graph it. Very simple trig function. So here's one period of the x coordinate graphed, and right beneath it I'm going to graph the y coordinate. Okay, so right beneath it I'm going to graph the y coordinate. The y coordinate is y equals sine of t. So the x coordinate was x equals cosine of t. The y coordinate is y equals sine of t. And sine of t and cosine of t, the graphs are identical in shape. They're just out of phase from one another. We know that from trig. So here's approximately what the sine function looks like. Okay, I want to kind of line them up time-wise. Here we go. Here's 3 pi over 2. Here's 2 pi. Okay. Pi. Okay. So, as t goes from 0 to pi over 2, just concentrate now on the x coordinate. As t goes from 0 to pi over 2, oops, still an eraser here. As t goes from 0 to pi over 2, that's indicated by little green arrows along the t-axis, the x value goes from 1 to 0. X value goes from 1 to 0. So put that in the corresponding xy plane above. As t goes from 0 to pi over 2, just the x coordinate, only the x coordinate. The x coordinate goes from 1 to 0, so the x coordinate is going to do that. Simultaneously, as t goes from 0 to pi over 2, the y coordinate, now look at the y graph, the y coordinate goes from 0 to 1. So as t goes from 0 to pi over 2, the y coordinate increases from 0 to 1. Okay, so now translate that idea to the xy plane above. As t goes from 0 to pi over 2, the y coordinate goes from 0 to 1. Now I've drawn these little arrows along the x and y axes, but the particle's on the curve. If this is a particle moving along the curve. The only way the x can go from 1 to 0 and the y goes from 0 to 1 is if we trace the curve in the counterclockwise direction. And you can convince yourself that the curve is not just the circle in the first quadrant. We get the entire curve, the entire circle, over and over and over again, traversed starting at the point 1, 0, and move counterclockwise. We can do this very briefly. If we continue on with time and looking just at the x coordinate, as time goes from pi over 2 to pi, the x values go from 0 to -1. X values go from 0 to -1 as time goes from pi over 2 to pi. At the same time, the y coordinate goes from 1 to 0. The y coordinate goes from 1 to 0. The only way we can do that and stay on this curve is to continue on the curve in the counterclockwise direction. Okay, if you keep looking at this quadrant by quadrant, as you go from 0 to 2 pi, we get the full circle. So why doesn't how do we know the particle doesn't stop? We know the particle doesn't stop, and it just keeps going around and round and round and around this circle throughout all time, starting at 0, because x and y are periodic functions. Sine and cosine are periodic functions with a period of 2 pi. So at every interval along the t-axis of 2 pi, we're going to get a new revolution of this circle. Okay. So let's take a look at another example. Let's get into R3. Let's take a look at, let's see, how am I framing this here? I should be a little more precise. So, example. Now let's do a different one. Sketch R of t equals cosine of t, sine of t, 1. 1 for the z component. Okay. So immediately, what does this mean? It means that the parametric equations are cosine of t and sine of t, and we already know what that means with x and y. This means that x and y stay on the unit circle, and we can go back and say t greater than or equal to 0 again. X and y stay on the unit circle and move in the counterclockwise direction. So x and y are staying on a circle, but z has to equal 1. Z equals 1. What's the equation z equals 1? If we didn't have anything else, just z equals 1. What is that? That's a plane. It's a horizontal plane, 1 unit above the xy plane. So this is saying that the x and y stay on a circle, but z must equal 1. The x and y stay on the circle, but z must equal 1. So in the translation of that into 3 space gives us, oops, God, I gotta get out of the eraser mode. The translation into 3 space says, well, if it was just in 2 space, x squared plus y squared equals 1 would look like this, where this is 1, 0. Finally starting to be able to draw things a little better. And would be traversed in the counterclockwise direction. That's if we were in the xy plane, but we're not in the xy plane. We're in 3 space, and on this particular curve, z must always equal 1. So we go up 1 and move that circle up there. X and y stay on the circle. The z coordinate pushes everything up to 1. So the actual curve, I'm going to draw solid here. The actual curve is the circle. The unit circle shifted 1 unit up, traversed in the counterclockwise direction. That's the graph of this space curve. This space curve is a circle that lies in the plane z equals 1 and is traversed in a counterclockwise direction. Okay. So now let's up this a little bit. Let's step up our game a little bit. I would like I would like to write a word before. Okay, here we go. I would like to sketch a new curve where x and y still stay on the circle. Oops. Where x and y still are staying on the circle. X squared plus y squared equals 1. That means x equals cosine t, y equals sine of t. Still traversed in the counterclockwise direction. Still starting at the point 1, 0 in the xy plane. But I don't want the z value to be 1. I don't want the z-value to be 2. I don't want the z-value to be 0. I want the z-value to also change. Okay. Now, think about what this means. X equals, graphically, x equals cosine t, y equals sine of t. Okay, so this says, again, that the x and y stay on the circle x squared plus y squared equals 1. But the z-value is changing with time, so we're not staying in some sort of fixed plane, z equals 1 or whatever. In fact, the z-values are moving upward at a constant rate. Why is that true? Z is increasing at a constant, and I'm going to, for a hint of how you're going to answer how you can answer my question, I'm going to put the word rate in bold or in caps and then underline it. The z is increasing at a constant rate. Why? 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 Because dz dt is 1. Okay, so the z-value is increasing at 1 unit in the z direction per second, per whatever the units of t are. Okay, so now think about this. X and y stay on a circle, but the z-value increases at a constant rate. So the curve itself, the whole curve, not just the x and y, lies on a what? Lies on a three-dimensional what? A what? The x and y stay on a circle, but the z-values increase. The curve lies on a cylinder. In fact, it lies on, I'm going to take off the word a and put in the word the. Cylinder, x squared plus y squared equals 1. It's an equation of a cylinder. To remind you, if you don't remember, that's the equation of a cylinder. You're missing the z value, so the cylinder extends in the z direction. So the curve lies on a cylinder. Where does the curve start? Well, r at 0 equals cosine 0, sine 0, 0. Remember, t is the z coordinate. Cosine 0 is 1, sine of 0 is 0, and 0 is just 0. So the curve starts at the standard basis vector I, 1, 0, 0. The curve starts at 1, 0, 0. The x and y stay on a circle, so the curve stays on the cylinder, and the z-value increases, I'm underlining the word increases, at a constant rate. That means the z-values are going up. What is this curve? What is it? What does it look like? What does it look like? What does it look like? And I'll give you a hint. It's in your DNA to understand what it looks like. It's a helix. It's called a helix. If you haven't heard that term, don't worry about it. Let me show you what this curve looks like. The curve lies on a cylinder, x squared plus y squared equals 1. So here's the cylinder, x squared plus y squared equals 1. Let me redraw the base here. Solid, and then we can't see it, that part. Okay, so here's the cylinder, x squared plus y squared equals 1. Let's introduce some axes here in, maybe say blue. So here's the y-axis. Here's the z-axis. Here's the x-axis. X, y, z. Now I'm going to draw the actual curve in red. This is the point, oops, and suddenly I go back to blue. All right. This is the point 1, 0, 0. Now the x and y are doing this. The x and y are going round and round and round and round and round in the counterclockwise direction. But at the same time, z is increasing at a constant rate of 1. What's the net result? The net result is that we're getting this kind of graph. We're staying on the cylinder. Okay, and we're moving using arrows to indicate. The x and y are moving around the circle in the counterclockwise direction, so we must be twirling around this thing, up this thing in the counterclockwise direction. So we're going up this curve. This curve is called a helix. It's a very important curve. It's a very important curve in the study of genetics. Apparently our DNA lies on several of these curves. Notice how I didn't say several and then name the curves. The plural of helix is not helixes. Helix is helices. Helices. I promise I won't mark off on a test if you write helixes. Okay, it's one of the few things I won't mark off on a test for. Okay, so this curve is a helix. It is a helix, a helix, a helix, a helix. So what would change? I don't think I need to draw too many more of these before we move on, but what would change if I had the curve 2 cosine t, 2 sine t, 5t? What do you think would be different? Would it still be a helix? Yes. X equals 2 cosine t, y equals 2 sine t, x over 2 squared plus y over 2 squared equals cosine squared t plus sine squared t equals 1. And of course, z equals 5t. Let's say z was negative 5t. So the curve lies on a circle again, circle of radius 2. Circle of radius 2. So actually even better, the curve lies on a cylinder, vertical cylinder of radius 2. Oops. Vertical cylinder of radius 2. Let's say t is greater than or equal to 0. Okay, so I'm going to draw in the axes again. What did I use for axes? I used blue before. I'll use blue again. So here's the y-axis. Here's the z-axis. Notice, look at what I'm doing. Oops, don't want the arrow down there. Positive z is still upward. Oh shoot. Positive z is still upward. Okay. Fix this a little bit. Okay, so here's z, here's y. Look at what portion I'm graphing. I'm graphing below the xy plane. Why? Look at the z coordinate. Z is less than or equal to 0. If t is greater than or equal to 0, if time is greater than or equal to 0, and I believe I made that clear, that makes negative 5t less than or equal to 0. It also makes dz dt negative 5. So the z is decreasing. If the derivative of a function is negative, a function is decreasing. Okay, so the object, if you want to view this as a particle moving along this curve, is moving along the curve in the shape of a helix. And the x and y are being traversed in the counterclockwise direction, but the z values are moving downward. I don't know if I could draw that. I'm going to try. I'm just making up this example, and I shouldn't do that. Let's see. Okay, I'll try. All right, I think it worked. It worked. Okay, so the actual curve is the helix that's moving downward. Now, I'm hoping that you can see it okay. Okay, so let's move on here. Let's do another example. Mostly an algebraic example for our next example. So example, find parametric equations. You're going to be doing a lot of these kinds of examples in your homework, and this is a very basic one. So find parametric equations for the curve of intersection of z equals x squared plus y squared and x equals 2. Okay, so let's tear apart what's going on here. Each of these equations is a surface. The equations on their own don't represent, these equations on their own don't represent curves. They're surfaces. First one is, and think about what it is. You should know this by now. If you finished your homework, or at least started the homework from the last section, should be done with it by now. But if you started the homework from the last section, z equals x squared is a what? It is a paraboloid, and x equals 2 is a vertical plane, 2 units in front of the YZ plane. So what's going on here is we have a paraboloid. We have a paraboloid, and we have a plane that's slicing through that paraboloid. We have a paraboloid, z equals x squared plus y squared, and we have a plane, 2 units in front of the YZ plane. Here's x equals 1, x equals 2. And that plane, vertical plane, will slice into this paraboloid in the shape of what? Here it is. This is the curve of intersection of the plane x equals 2. Here's part of the plane, x equals 2. Let's see, here's part of it. My drawing didn't turn out real nice, but they rarely do. So the curve of intersection of a vertical plane and a paraboloid is a parabola, should be a parabola. How can you know that for sure? Well, how do you find the intersection of 2 surfaces? You stuff one into the other, stuff the equations of one into the other. So if I let x equal 2, I get z equals 4 plus y squared. That's the equation of a parabola that opens up in the YZ plane. Of course, we're not in the YZ plane. We're 2 units in front of it. This is a parabola. This is a parabola. Okay, we didn't answer the question. We didn't solve the problem. It said find parametric equations for the curve of intersection. That means I have x as a function of t, y as a function of t, and z as a function of t. I have to introduce the parameter. It's very easy to do this. X as a function of t is x equals 2. Okay, x equals 2 is x equals 2. It's a constant function of t. However, z should equal y squared. Z should equal y squared. I'm sorry, z should equal 4 plus y squared. Z should equal 4 plus whatever y is squared. So I'm going to make y equal to t. You can do that. You can make y equal to t cubed if you want. You can introduce a parameter and for y equals t, and then z must be equal 4 plus t squared. There are perfectly good parametric equations for this parabola. Okay. For the rest of the lecture, we're going to start getting into some of the calculus of vector functions. This is a calculus course, and basically we've looked at some vector function algebra. We need to get some calculus. So if, let's say, r of t, first is really kind of boring and easy here. If r of t is given by component functions f of t, g of t, and h of t, okay, then we define the limit as t approaches time a of r of t to be nothing more than the limit of the individual component functions. The limit of f of t as t approaches a, g of t as t approaches a. So we get some nice stuff happening here. Don't get used to it. No, I'm just kidding. All of this stuff I think is nice. That's how we evaluate limits. Okay, so for example, the limit, let's say, let's do this. Let's say its limit as time goes to infinity of e to the negative ti plus, let's say, t minus 1 over t plus 1 j plus the inverse tangent of t k. This is equal to nothing more than the limit of e to the negative t is, as t goes to infinity, e to the negative t goes to 0. So this approaches 0. We'll do that with an arrow. This approaches 0. So 0i. T minus 1 over t plus 1 approaches 1. So j. And this is a good test from Calc 2, if you remember about the inverse tangent function. What does the inverse tangent function do? The inverse tangent has a horizontal asymptote at pi over 2. So plus pi over 2k. So the limit of this vector valued function, this curve, is the constant vector 0, 0i plus j plus pi over 2k. Okay. Okay, so what does it mean for a function to be continuous? Continuity. We only look at limits and continuity briefly in this course, just like in Calc 1. Continuity. R of t, a space curve, is continuous at t equals a if the limit of r of t as t approaches a is r of a. It's the same definition, the same looking definition as in Calc 1. So we have a vector function, some curve. It's traversed in that direction, whatever. And let's say r of a is this red vector I'm going to draw. This is r of a. R of a is not necessarily a position vector. R of a can be, I'm sorry, I misspoke. R of a doesn't necessarily have to lie on this curve, the curve that I've drawn. R of a can shoot past it. So that's the point on the curve R of a. Let me draw it a little smaller. I don't want it to look, I'm losing perspective here. Okay. I'll start over that. Here's R of a, that point right there, R of a. And on the curve, there's a hole there. So this curve is not continuous at t equals a, because as t approaches a, the curve is moving in this direction, this direction, this direction, this direction, this direction, and approaches the little circle. And then right at t equals a, the curve shoots through the circle. As t approaches a, r of t is staying on the curve, and then right at t equals a, the r of t, the position vector, shoots right through the curve to a new position. But if those two things are equal, if the limit of r of t, that is if the position vectors are approaching the same thing that's actually there right at t equals a, r of a, then you have continuity. Then you don't have that punctured effect. Okay. Well, what that does, my good students, is that ends section 13.1. But this video segment covers two sections, 13.1 and 13.2. So I anticipate another half hour to 45 minutes. That might be a underestimate. So if you want, you might want to pause the video or take a break and come back. Or if you want to power through it, then just power through it with me. But I'm going to use some video magic and take a break anyway. So I'll see you in about 1 second. I don't need a break. I'm just going to go. No, I'm just kidding. I took a 10-minute break and I'm back. So let's take a look at section 13.2. Let's analyze the concept of derivatives and integrals, mostly derivatives, and integrals of vector functions. We need a derivative. We need a calculus. Well, we have limits, we have continuity. Mostly limits and continuity are an afterthought for us. We just like in Calc 1, we don't spend too much time on limits, but we do spend a lot of our time and energy talking about what derivatives and integrals mean. So here's a definition. Here is a definition. Let's say, given a vector function r of t, we define r prime of t, this thing we call the derivative of r of t, as, and it's going to look real similar to the definition of the derivative of a scalar valued function, or a scalar function, which the limit as h approaches 0 of the difference quotient r of t plus h minus r of t over h. It looks just like, or at least very similar to, the derivative of a function f of x. Okay, so now we get to the important part of the derivative. It's geometric interpretation. This derivative holds a lot of physics together. This derivative is really, really, really important. So to get a geometric interpretation of this, we're going to consider a curve in R2. This extends to R3. It's just easier for me to draw in R2. So here's a specific curve in R2, a vector function in R2. Okay. Here's x and here's y, and I want to redraw it. In fact, I think I want to draw it a little bigger, just so I can have more room to work. Okay, give me a second here. So here, a little bigger. It's a lot bigger, huh? Okay. And here's our curve. I guess I should get out of eraser. Here's our curve. R equals r of t. And let's say this position vector I'm going to draw right now in red. This is the position vector at some time t. R of t. And let's assume that at some time t plus h, t plus a little bit later, the position vector is here. So this new position vector is r of t plus h. What I would like is the displacement vector, or the vector from the tip of r of t, to the tip of r of t plus h. I want this vector right here. Well, remember from earlier in the course, if we have a vector A and we have a vector B, and we place them tail to tail, then the vector from the tip of A to the tip of B is what? It's B minus A. So that vector r of t, the vector from the tip of r of t to the tip of r of t plus h then has got to look like r of t plus h minus r of t. Okay. Now, what did the derivative give us in Calc 1? This should be an automatic for you. If it isn't, I'll tell you, or I'll remind you. What did the derivative in Calc 1 give us with respect to a curve? It gave us the slope of the tangent line. I would like the derivative, r prime of t, of a space curve to give us something similar to that. I'd like it to give us a tangent vector. Now, the vector I've just drawn just now, the difference r of t plus h minus r of t, that's not tangent. That's not tangent. It's sort of like a secant vector. That's not tangent. But what happens if I look at smaller and smaller and smaller values for h? I want to examine that question. I want to examine that question right now. So here's a redraw. The green vector now is the difference r of t plus h minus r of t. And it's not tangent. It's not tangent. It's approximately tangent to this curve. Now, look what, again, my question was, what happens to this vector, the green vector, that difference vector, as I look at h, smaller and smaller increments in time h? So if h is smaller, it seems reasonable that the position vector should be closer to the original position vector, not that close, closer to the original position vector. So this might be r of t plus h for a smaller value of h, increment in h. So the displacement vector, the green displacement vector, would now look like this. That's a better approximation to a tangent vector. Want a better one? Look at h smaller still. If h is even smaller, it seems reasonable that our new position vector r of t plus h is even closer to the initial position vector r of t. So as h approaches 0, that difference r of t plus h minus r of t appears to be getting closer and closer and closer to the tangent position to the curve. It seems to be approaching, so it approaches a tangent position. Tangent position. But there's a problem. There's a problem with that little green vector that's getting more and more tangent. What's happening to its magnitude? The problem is it is getting very small. In fact, it's shrinking to 0. That's a big problem. The whole idea with the derivative is to give us some sort of tangent vector. Now, how can I make that little green vector that's getting smaller and smaller and smaller? Oh my goodness, look what happens if I let h be even smaller still. Look what happens to the little green vector. I'll draw it blue because it's going to get lost in there. It's getting really close to the tangent position, but it's withering away to nothing. Okay, how could I take those little green vectors, and ultimately that little blue one, that I fit in there, how could I retain their tangent position, tangent approaching position, that is, I keep the direction of r of t plus h minus rt. It's becoming more and more tangent. But I don't let them shrink to 0. I make them longer. How do you make a vector longer? Well, keeping its same direction. How can you take a vector, a given vector that might be real small or might be real big, and increase its size while retaining its direction? You multiply it by a constant. So I would like to multiply this quantity by a constant to make it longer so that it approaches the tangent position. That little blue vector, which I really should have drawn in green, oops. That little blue vector is approaching the tangent position. I'd like to get rid of that little blue vector. It didn't work. But it's shrinking down to nothing. So how can I, let's see, in another color, how can I take that little blue vector and make it bigger again? I take that little blue vector, that difference, in fact, I wrote the difference in black. I'm going to change it to blue. There's the little blue vector. How can I make it into the longer yellow vector? Same direction. I multiply it by a constant more than 1. Well, think of a constant related in here that's more than 1. I think I will use as that constant 1 over h. H is getting small. H is approaching 0. So 1 over h is getting big. Okay, 1 over h is getting big. That means it's more than 1. So that multiplying by 1 over h lengthens that little blue vector, that little blue difference. Hopefully, in the limit as h approaches 0, that the yellow vector that I've drawn, that one that's approaching the tangent position, doesn't get too big. If it doesn't get too big, then I get the derivative. This is the reason why we have this derivative the way it is. If I write this in the simpler notation, this is just the limit of r of t plus h minus r of t over h. That is r prime of t. And in the limit, it should look something like this vector that I'm going to draw in a nice bright red. It should approach a tangent vector. That is r prime of t. R prime of t, this vector is tangent to the curve, tangent to the curve, r of t, and it does one other thing. I never put the direction of the curve. I kind of implied it with all those arrows shrinking back toward r of t. But we're assuming the direction of the curve was, let's say, counterclockwise. So r prime of t is approaching the tangent position, and it's also points in the direction of increasing t. Points in the direction that the curve is flowing. Points in direction of increasing t. It has much more meaning in physics than that. Then it's more than just tangent and pointing in the direction of increasing t. That's a lot of what 13.3 and 13.4 are going to be based on, especially 13.4. The r prime of t, if this is a particle moving along a curve, actually gives us the velocity of the particle. Okay. And other things. The second derivative will give us acceleration and stuff. But that's really in our future for the next couple of videos. Okay. So A couple of things. First, we need an easy way to find r prime of t. Easy, quote unquote. So, theorem. We won't prove this theorem. We'll just state it. R prime of t is the vector whose components are x prime of t, y prime of t, z prime of t. So there's the formula that we actually use most of the time for finding r prime. If you want the derivative r prime of a vector valued function of a space curve, just simply form a new vector with the derivatives of the components, the component functions. Okay, notation. We don't always use the same notation. R prime is the same thing as writing dr dt. It's the same notation we use in Calc 1. Or the same thing is, this is called operator notation, d dt of r. Okay, those are pretty standard. Okay. Alrighty. Before we move on to a specific example, there's one other vector that's associated with r prime of t. If this is our space curve, and this is r prime of t, r prime of t, and let's say the curve is in 3 space. So here, oops. So here are the axes. So we're looking in the first octant. So here's the vector r of t, position vector. R prime of t is tangent. So r of t is a position. R prime of t is tangent. There are times, actually there are a lot of times, when I'm not interested in all of r of t. All I'm interested in is in its direction. If you're only interested in the direction of a vector, you can create something called a unit vector. Okay, so r prime of t is often referred to as the tangent vector to r of t. If I take r prime of t, and divide by its own length, assuming that the length of r prime of t is not 0, then I get a new vector, and that vector is going to be of length 1. I'm going to get a tangent vector, and we use the variable capital T to indicate that. Now we don't need to draw a little hat over that, because simply drawing or writing capital T means we're looking at a unit vector. But there's nothing wrong with writing capital T and a little hat over it to indicate a unit vector, but it's not necessary. It's already indicated by the fact that we're using the letter capital T for this unit vector. Capital T is called the unit tangent vector. This is the unit tangent vector. And the only thing it does for us for right now actually is it points in the direction of the curve. It has length 1. So just to actually put a copy of it in our drawing, I'll say it's in blue. Here's T. Here's T. The only thing it does is grabs the direction of r prime of t and has length 1. It's a unit vector. So it's a unit tangent vector. All right, so let's take a look. Let's take a look at a specific example. Yeah. Let's see here. So here's our next example. Consider the vector function r of t equals 2 sine of ti plus 3 cosine of tj for t greater than or equal to 0. So we're in 2 space, and we can consider this as an object moving in space, a fly moving in the xy plane. So the first thing I'm going to do is I want to sketch the curve defined by r of t. So this is what we did in the last section, this type of thing. So I'm going to write the parametric equations for this vector valued function. So x equals 2 sine t, and y equals 3 cosine t. How can I get rid of the parameter? Well, we're going to use that sine squared plus cosine squared equals 1 little trick. So we're going to have x, if I take x and divide by 2 and square that, if I take y and divide by 3 and square that and add those things up, I'm going to get sine squared t plus cosine squared t, and that's 1. So that's the curve. That gives us the curve on which we lie, on which this fly is buzzing through the xy plane. Sort of looks like the homework or the exam ellipse. Sort of. Might even be the exact one, I can't remember. So we have x squared over 4 plus y squared over 9 equals 1. This is a standard form of an ellipse. Its major axis is vertical, since 9 is bigger than 4. Let's take a look at the graph. So here's the xy plane. Look under the x variable, we have 4. It's square root of 4. There are two square roots of 4. They are plus and minus 2. So along the x-axis, I'm going to move plus or minus 2. Under the y term is 9. Square root of 9 is 3. So I'm going to move plus or minus 3. 1, 2, 3 in the y direction. 1, 2, 3. And since this is a standard form of an equation of an ellipse, I'm going to draw the ellipse. I've never been able to draw an ellipse once. I usually have to erase it and redraw and redraw. Let's see what I can do here. Most of my problem with the ellipses is getting it to look symmetric. We'll see. Oops, there it is. Let's see if I can do this. It's not going to do it, so I'll just be satisfied with what I can do. Here, that's the best I'm going to do. I want to retry this piece in the first quadrant. Probably be better if I didn't, but well, we'll see. Let's see. It doesn't turn out much different. Okay, we'll leave it. So there's the ellipse. What's missing? Starting point and direction. Where does this thing start? Where does this thing start, and what direction are we moving? Well, at t equals 0, what is the position vector? R of 0 is 2 times the sine of 0 is 0, so it's 0i. 3 times cosine of 0 is 1, so plus 3j. So we're on the y-axis. So we're starting on the y-axis. And we're either moving clockwise or counterclockwise. Well, let's take a look. Take a look back up at the beginning of the problem. See if I can fit this in real small. X is 2 sine. Here's the x coordinate versus t. If this doesn't work out, I'll draw them bigger. Cosine. Yeah, it's not the worst looking axis I've drawn today. Doesn't much better. So okay, we'll take it. So the cosine goes from 3 to 0, then to -1, then to 0, then to 3, -3, and then I think I said -1. So the y value goes from 3 to 0, x value goes from 0 to 2. So x value stays between -2 and 2, y value between -3 and 3. Notice that the x value is increasing from 0 to 2. So I can temporarily make that bigger so you can see that. So the x value is increasing initially from 0 to 2, while the y coordinate is decreasing from 3 to 0. Make that smaller back again. So x value increasing, y value decreasing. The only way that can happen and us start at the point 0, 3 is to move in the clockwise direction. So this guy is moving in the clockwise. This particle is moving in the clockwise direction. Clockwise direction. Okay. So the next part of the problem. Oops, sorry about that. Next part of the problem. Next part of the problem. Find r prime of t. well, I keep popping up as keyboard. Sorry about that. R prime R of t was 2 sine of ti plus 3 cosine of tj. Just as a reminder, R was 2 sine ti plus 3 cosine tj. So R prime of t is 2 cosine ti minus 3 sine tj. Remember, to find the derivative of a vector valued function, you just take the derivative of the component functions of the position vector. Okay, pretty straightforward. So next part, here's where it gets a little more interesting. Sketch R of t and R prime of t for t equals pi over 3. Okay, well, R prime of t was 2 cosine ti minus 3 sine tj. R prime was 2 cosine ti minus 3 sine of tj. So R of pi over, I can find R prime first. R prime of pi over 3 then is 2 cosine of pi over 3i minus 3 sine of pi over 3j. And the cosine of pi over 3 is 1/2, so this is 2 times 1/2 I. Sine of pi over 3 is radical 3 over 2, so minus 3 times radical 3 over 2j. So we're looking at I minus 3/2 radical 3/2 radical 3j. Okay. This is approximately equal to, let's say, I minus 2.6 j. I'm approximating it so that I can get kind of an accurate picture of the graph in the actual graph of our curve. Okay. I also need R of pi over 3. So R of pi over 3, I'm kind of going backwards here. I'm finding R prime first. R of pi over 3 is 2 times the sine of pi over 3 I plus 3 times the cosine of pi over 3 j. Sine of pi over 3 is still radical 3 over 2, so this is radical 3i. Cosine of pi over 3 is still 1/2, so minus 3/2 j. And radical 3 is approximately, what is radical 3 approximately equal to? It's about 1.7, approximately, minus I minus 1.5 j. Okay, now just off to the side here, I computed the length of these vectors. So the length of R prime of pi over 3, again, this is just getting ready to graph these. The length of R of pi over 3, it's approximately 2.3. You'll see why I'm finding these in a second. The length of the derivative, the tangent vector at pi over 3 is approximately 2.8. Okay, so now let's get to the graph. So here's our original ellipse. I've took off the direction just so we can graph these vectors without having to look at the arrows for the direction. The position vector is I, where is it? There it is. It's 1.7 I minus 1.5 j. Actually, I think it should be plus 1.5 j. You probably caught it and are probably going crazy thinking, why are you writing that negative? Okay, 1.7 I plus 1.5 j. 1.7, this is 1, this is 2. 1.7 is about right here. 1.5 is about right here. So it's matching up, kind of almost. So here is, I'll do this in red, here is the position vector R. I won't write of pi over 3, it won't fit in my drawing. The tangent vector is I minus 2.6j. So it's 1i. That's one unit to the right, and 2.6 down. So from 1.5, I'm going to go down 2.6. It's like about that far down, approximately. So the tangent vector, this is just eyeballing this. It's like the ugliest tangent vector. Tangent vector looks about like this. Ugh, it's terrible. It's okay, I guess. Okay. I found their lengths earlier, so I could see how they would compare if I actually drawed them or drew them. Here's R prime. R has a length of about 2.3. R prime has a length of about 2.8. So R prime looks a little long according to what I've drawn. At least I've drawn R prime actually tangent looking. But there you go. There's the R is a position vector, R prime is a tangent vector, and R prime is pointing in the direction of motion. Okay, as I mentioned, R prime is going to have much more meaning for us. It's going to actually give us the velocity of the object or particle or whatever. I'm going to look at one more example, but this example is going to be in 3 space. So here's our example. Find parametric equations for the tangent line to the helix. R equals the vector whose components are cosine of t, sine of t, and t at the specific moment in time when t equals pi over 2. When t equals pi over 2. So what's going on graphically? So here's the cylinder, vertical cylinder of radius 1. I'm just drawing that ellipse basically we looked at about an hour ago or hour or more ago. If we assume that t is greater than or equal to 0, which I actually didn't write in this problem, if we assume time starts at 0, then as we got before, the helix then looks something like this. It continues on and on and on and on. So I'm interested in, back to the question, find the parametric equations for the tangent line to the helix at when t equals pi over 2. Well, if you're interested in any line, you need 2 things. You need a point and a direction. Okay, you need a point and a direction. So let's identify those things. You need a point or an initial position vector, an initial point or position vector, R sub 0. Is given by R sub 0 equals the position vector on the helix at the time in question, pi over 2. And that's nothing more than cosine of pi over 2, comma sine of pi over 2, the vector whose components are, and pi over 2. So that gives us cosine of pi over 2 is 0, 1, and pi over 2. Okay, which is no great surprise. I'm going to draw that initial position vector in green. And I missed my helix entirely. That position vector gives us into the YZ plane. Well, t equals pi over 2, we are at x equals 0. So that position vector should be easily placed in the YZ plane. Okay, cool. So that's working out nice. What do you think should be involved with? It's kind of a difficult question, I guess, but I'll put it anyway. One of the coordinates of the direction vector should be 0. Which one? Which one? Well, if we're on the right edge of this helix, or on this which is on the cylinder, if we're on the right edge of the cylinder, the tangent vector needs to have one of its coordinates 0. The tangent vector cannot have a non-zero y component. the tangent vector should be in the direction of the xz plane. We're on the right edge of this cylinder, so we should be in the direction of the xz plane. Okay, so if I wonder if I can draw that. Here's a portion of the xz plane in blue. I'm taking a big chance here. Here's a portion of the xz plane in blue. This is not, I didn't plan on this part of the lecture. Right there, xz plane. That portion of the xz plane can be placed tangent to the helix on the right edge of the cylinder where we are actually located. So the actual tangent plane, I hope this works out. It's actually working out better than I thought. Here's the actual tangent plane on the edge. I've just basically translated that portion of the xz plane over. Okay, that tangent plane is parallel to the xz plane, so it should have the tangent vector should have the y component 0. Well, let's move on here. We need a direction. A direction for this tangent line. The direction should be r prime at the time in question, r prime at pi over 2. Okay, well, r was cosine t sine t t, so r prime tangent vector should be negative sine of t. Derivative cosine is negative sine, derivative sine is cosine, and derivative t is 1. So specifically, r prime at pi over 2 should equal negative sine pi over 2 cosine pi over 2 comma 1, or negative 1 0 1. This tangent vector is parallel to the xz plane. Negative 1 0 1. How can I actually draw that in here? I'll draw it in green also. It's not going to look very nice. Negative 1, negative 1, positive 1. It's not going to look very nice. There it is. That's all we're going to get. There's the tangent vector. I'll draw the tangent line, actual tangent line in there. Maybe that'll make things look a little better. Here's the tangent line. It's actually turning out better than I thought. Okay. I'll draw a little negative 1 for the y component, or x component, rather, of the tangent, and positive 1 for the z component. Okay. Worked out sort of okay. All right. Let's find the equation of that, the parametric equations for that tangent line. Remember, parametric equations look like x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. So our equations look like x equals the x component of my initial position is 0. The x component of my direction vector is negative 1. Y equals the y component of my position vector is 1. The y component of my direction vector is 0, so y equals a constant 1. Okay. The z coordinate, the z equation, or my parametric equations, is the initial z value, pi over 2, plus the z component, third component of my direction vector t. So there they are. These are the parametric equations of that tangent line. Okay. Okay. So I wanted to end this lecture with a couple of things. First, a short list of formulas. These are in your textbook. I think I wrote in my notes, they're on page 898 of the 8th edition of the textbook. But there are formulas that sort of corresponding formulas from Calc 1 for derivatives. So let's take a look at some of those. Let's see here. I want to change colors here. So formulas. Formulas. First, if you want the derivative with respect to t, often referred to as a time derivative, by the way, in physics. If you want the time derivative of u plus v, it's nothing more than the time derivative of the first plus the time derivative of the second. So it's kind of a nice, obvious one. Okay, if you want the time derivative of a scalar multiple of a vector function, these vector functions are u of t and v of t. The scalars factor out, just like they did in Calc 1. Okay, now we get one that's pretty elaborate. It doesn't have a complete Calc 1 analog. Close. Scalar function times, not dot product, not cross product, just times vector function. This looks like the product of two functions, but it is, but it's a product of two very different kinds of functions, a scalar function with a vector function. Well, we have a product rule, and it has to be written this way. It's the derivative of the first times the second times the vector function plus the scalar function times the derivative of the vector function. Since it doesn't make any sense to write u of t times f of t, we don't. It just makes no sense. Remember, there's no such thing as a vector times a scalar. u5 doesn't have any meaning. So let me get rid of that stuff. So the order is kind of important, the way we write this. Okay. So we have the derivative with respect to t of the dot product of u of t with v of t. That is the derivative of the first dot with the second. I'm leaving the of t's off, plus the first dot the derivative of the second. So it's what we expect. Okay, 5. We have a similar formula for the cross product, the time derivative of the cross product. I'm omitting the of t's now, the of t's, the parentheses t's. It's derivative of the first cross the second plus the first cross the derivative of the second. Okay, and finally in this list we have a sort of chain rule. Vector function of scalar function. Vector function of scalar function. And the formula is pretty much the chain rule, looks like the chain rule in Calc 1. It's the derivative of the outside function, leave the inside function alone. But then we have to write the derivative of the inside function first because we don't have vector times scalar. Okay. Arrow. Okay. Okay. Well, let's see here. Let's finish this lecture off with integrals. We will not take the amount of time that we took with derivatives. This goes fairly quickly. Integrals. Integrals. Okay. So, if r of t equals x of t, vector whose components are x of t, y of t, and z of t, I'd like to be able to integrate both indefinite and definite integrals. The indefinite integral of r of t is nothing more than the indefinite integral of x with respect to t, the indefinite integral of y with respect to t, indefinite integral of z with respect to t. What do you think's missing? Plus a constant. What's wrong with it? you can't have a constant plus a vector, so it's a constant vector. Okay, the same thing holds true with definite integrals. So if I replace all these, if I replace the indefinite integral with a definite integral, I'm attempting to be lazy here, so I'm going to see if I can copy it and paste it. We'll see if it works. Okay, cool. So if I replace the definite integral with the indefinite integral with limits, then I replace the components with definite integrals. And we lose, what do we lose? Constant integration, okay? This is kind of cool. Okay. All right. I think that ends the lecture, but I want to do one more really quick example. For example, really quick, I promise. So if R is the position vector or the vector function whose components are 1 over t and 2t, then the definite integral from 1 to 3 of R dt is the definite integral from 1 to 3 of the vector function 1 over t 2t with respect to t equals the vector whose components are the integral from 1 to t of 1 over t dt. And second component, oh, that's the weirdest integral sign. Second component is the integral from 1 to 3 2t. Okay, so this is the natural log of 3, and the integral of 2t is t squared. T squared from 1 to 3 is 9 squared minus 1 squared. I'm sorry, 3 squared minus 1 squared. 3 squared is 9, 1 squared is 1, 9 minus 1 is 8. So just to give you a specific example. We're going to see a lot of examples coming up soon. So that's it. That's it for this video segment covering the first two sections of chapter 13, 13.1 and 13.2. I recommend that you get started on homework as soon as you can, and as always, I'm looking forward to talking with you all again soon.